Hey everyone, welcome back, and today let's solve Leetcode problem 3396, titled Minimum Number of Operations to Make Elements in Array Distinct. So we're given an integer array nums, and we need to ensure that the elements in the array are all distinct. And to achieve this, we can perform the following operation any number of times. We can remove 3 elements from the very beginning of the array as a prefix, if you will, and if the array originally or initially at that point has fewer than 3 elements, we then have to simply just remove all the remaining elements, whether it's 2 remaining elements or 1 remaining element. Note that an empty array is considered to have distinct elements, really none, if you will, and we want to return the minimum number of operations needed to make the elements in the array distinct, i.e. each element in the input has a frequency of exactly 1. It doesn't have any duplicates that we haven't seen before. So in example 1, we have our input array nums to be the following. And in this case, the reason why we have an output of 2 is because that is the minimum number of operations that we need to apply on this array, basically removing the prefixes of 1 and 3, or the first 3 elements, to get all the elements of the array to be unique. We can remove this 1, 2, 3, but we'd still have these 2 3s, so we have to remove this 4, 2, 3, then we'd have 3, 5, 7, and note how 3, 5, and 7 are all distinct elements. They're all distinct in value, unique in value. They all have a frequency of exactly 1, and that resulting 3, 5, 7 array. Notice how that took us 6 divided by 2, or 6 divided by 3 rather, or 2 operations, hence the reason why 2 is our output. We could have also technically removed this 3, 5, 7 and still would have had an empty array, which still would mark, a non-duplicate elements, but we want to minimize the number of operations, hence we'd only make that operation be 2. In example 2, we have our input array nums to be 4, 5, 6, 4, 4. In this case, we actually need both operations. We remove this 4, 5, 6. We only have 2 elements remaining, so we just remove these 2 elements 4. And we would actually have an empty array, but that's still considered to be just a distinct array to get all the duplicates out of the way, and so 2 is the minimum number of operations. If we just remove the 4, 5, 6, we'd still have 2 4s. There are still duplicates, and so we still have to remove those elements as well. Finally, in example 3, we have our input array nums to be 6, 7, 8, 9. We don't have to do anything here. Why don't we have to do anything here? Well, because all the elements are initially in the input array are already all distinct, and so we simply just have to have an output of 0. We already have a perfectly distinct array. We don't have to do any operations. We don't have to remove any elements, and so we have an output of 0, right? We don't have to make any operations, or 0 operations. So for the constraints here, notice how they're actually quite small here. The length of our input array nums is always going to be between 1 and 100, and any value in the input array nums is going to be between 1 and 100 as well, which brings us to the main observation to really solve this problem. Whenever we see duplicates in the array, again, it's kind of like the main observation that we should be making. Whenever we see any duplicates in the array, we know we have to remove them. They're kind of, if you will, necessitate our removal operations, and so we have to get that out of the array. We don't want any duplicate elements that we've already seen before in the prefix or early part of the array, and of course we're removing, that is, the prefixes of the array. So if we ever encounter a duplicate in the array, that indicates that all the preceding elements have to be removed to ensure distinctness. For an example, if we had something like, 1, 2, 3, or 4, 3, 5, 4, if we see this 4 here, that's cool, we like that 4, but all of the 4s before have to be removed. And why all the 4s before? Well, and not after, well, because we're removing all the prefixes. And so, of course, we're going to remove these 4s first. And so to minimize the number of operations, whenever we see this 4 here, starting from the end of the array, all the 4s before that have to be removed so that this 4 is distinct. Right, that applies not just for this 4, but any other elements there are. In this case, 4 is really the only repeating element, but this is just a quick example to show what I really mean by all the preceding elements have to be removed to ensure distinctness of each element whenever we actually encounter a duplicate, which is really how we're going to solve this problem as well. And so how we're going to solve it, well, we're going to traverse the end of the array from the end of the array to the beginning of the array, and we're going to continuously track our seen elements. We'll use probably a set to do that for more efficient runtime, and we can always determine the point at which a duplicate forces an operation to remove a preceding element or a prefix of the input array. Right, so how are we going to solve this problem? Effectively, we're going to have a data structure to actually keep track of all the elements that we've seen as we traverse the array in reverse order, i.e. from right to left, and that's most likely going to be a seen set. And after we actually initialize that set, we're going to iterate through the elements from that order again, last element to the first element, and for each element, we're checking, is it already in the set? If it's already in the set, okay, well, of course, this is already a duplicate element. We have to remove it, and so we have to calculate the number of operations that we need based on its position. Otherwise, we simply add it to the this set and continue on like forward, right? So let's go ahead and see how this solution actually works in a whole. And like I was just talking about, let's first actually initialize our set. So I'm literally just going to call it scene, marking the number of scene elements or which scene elements that we've seen so far from the end of the array, right? Basically, it's only going to store our unique elements, basically meaning, of course, no duplicates, right? And effectively, we're going to use this to track all of the numbers that we've encountered so far while we actually loop from the end of the array, right? So give me a minute here. Let me just quickly mute my notifications, guys. Sorry about that. Okay, perfect. Now, once I get that out of the way. Now, after that, let's actually begin our iteration, i.e. our actual looping from the end of the array to the beginning of the array, right? Before we actually encounter our first duplicate value that we have to actually calculate the number of operations to remove for. So, not a standard for loop, we're going to start from the end of the array. So for I in the range, starting from the last element, which is calculated by the length of our input array nums minus 1, that's the last index of the final element in the input array nums, we're going to decrement by 1 each time, basically. In other words, we're going to go from up until the negative first or 0th index inclusive, and this is where we decrement by 1 each time, meaning go 1 index less or 1 index to the left each time, right? Effectively, we're going to go through reverse order from the last element to the first element to actually track the last occurrence of a duplicate very efficiently to remove all the preceding elements of that singular element to make sure that it's no longer a duplicate, where we find the earliest index from the back where we actually see a duplicate, and from that point onwards we'll know how many elements that we have to actually remove to make sure that it's a singular non-duplicate element after those removals, right? So here, now, if a current element nums that I, whatever it may be, if it's in our scene set, so if we've already seen it, if it is actually a duplicate, well, we have to actually remove it, right? We've seen that in the number, or rather in the set, we've seen this number before. It is a duplicate, and since we're going backwards, this is not the last occurrence. Since it's not the last occurrence because we've already seen this in a previous occurrence and it's already stored in the set, in the scene set that is, we've found a duplicate number and we have to remove it. It needs to be resolved. And so using our operation, let's calculate the number of operations that we have to make to remove this element here. It's going to actually be, and I'll explain this really quickly, the current index that we're at plus 3. Sorry, I don't know why I had a 1 there. And this is going to be integer divided by 3. Why 3? Well, because guess what? We remove 3 elements in each operation as a prefix of the input array at that position, right? So again, if we actually do find a duplicate at this index I, i.e. nums that I, we know we need to remove everything from the start of the array up until this index I to remove all the duplicate elements to make sure that our current element nums at index I is a unique non-duplicate element after the operations. And our formula here, if you will, kind of like the core concept of this solution, if you will, is we know one operation is going to remove 3 elements at a time. That's where that plus 3 comes into play, right? And so if you want to remove I plus 1 elements, because of course this is 0 index, we're going from 0 to I, so there's technically not I, but I plus 1 elements in that window, well then the number of operations would be I plus 1 plus 2 integer divided by 3. That's going to simplify to, of course, I plus 3 integer divided by 3. And of course, we immediately return that. We don't keep going on forwards because we want to return the number of operations needed, as we only need to find the first duplicate, right? Because once we find the first duplicate, that's going to be the last duplicate that we actually end up removing if we start from the beginning of the array. And so we don't have to keep going, right? That's going to be the final element that we eventually have to worry about if we iterate it in regular order. Now, if we haven't already returned yet, in each iteration, we want to, of course, add to our scene set nums at index I, as marking it as one more scene element in our set as we traverse backwards in the array. That way we can actually track it and detect its potential future duplicates while we actually continuously keep going as we loop backwards before we actually return any duplicate that we've seen last, right? Now, effectively, we're going to return 0 once this for loop is done executing, once it's done terminating. If we haven't returned any index or any duplicate in the input array, we're going to return 0, indicating that we didn't find any duplicates, and we simply have only no operations needed. Because, of course, all the elements are already distinct. We didn't find any duplicates and the loop already finished. We can simply return 0, meaning we don't need any operations, or we need 0 operations. And example 3 is a great case of this, where we already given an input array that has 0 duplicates. Right? So if I were to submit this, unless I made any syntax errors, or there should be accepted and there should be a valid solution, so let's go ahead and double check that. And as you can see, this really is just about as efficient as you can get it to be. So on a high-level rundown, how are we really solving this problem? Effectively, we're iterating after we initialize our scene set from the end of the array to the beginning of the array to actually detect the first duplicate from the back. Now, the moment we actually find a duplicate, we know that that's going to kind of be our bottleneck. We have to calculate how many chunks of 3 elements or windows of 3 elements we have to actually remove from the start of the array to eliminate that duplicate and go up until that index of removals. And by going backward, we're always ensuring that we catch the earliest necessary cut. Right, that's going to minimize the number of operations we want. And if, of course, no duplicates exist in the input array, and the traversal finishes, we simply return 0 because we don't need to perform any operations. That's what that return 0 really is for, right? So moving on to the runtime complexity here, it's actually going to be straight up linear. If you guys haven't noticed yet, it really just has a one-pass singular for loop singular traversal solution. We're only iterating through the array from once back to front. We're going to go through each element exactly once in worst case. And technically we do have some set operations like .add and return and whatnot, but those are all constant operations on average. Those are not going to affect our runtime complexity, right? And for our memory or space complexity, it's actually also going to be linear or big O of n. Why? Because look at this. We have our whole scene set array. In the worst case, that means we might actually store all the elements in the set if all of them are actually unique. Again, a good example would be example 3, and so of course on average this is going to be a big O of n or linear memory or space complexity. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel, and without further ado, I will see you guys in the next video. Bye bye.